Hello everyone, we're going to go through another example today. I've got it set up right here, so now we just need to work through it. Just like we've been doing in the past, we're going to solve this problem by the substitution method. So let's begin by taking what appears in the right-hand side, in this case it's n over 3, and plug it back into the equation. Just as we've done every time, we're going to give some designation to the equation we're going to be plugging into. In this case, we're going to designate it with a red bar. And we're going to plug n over 3 into the red barred equation. So plug n over 3 into the red barred equation. So let's do that. The left-hand side, we get t of n over 3 is equal to, plugging in n over 3 on the right-hand side, we get t of n over 3, which is n over 9, plus c n over 3, making sure to plug it into that additional cost as well. We're then going to substitute the bit I just underlined in red right there into the original equation for t of n over 3. So let's make that substitution. The left-hand side remains t of n equals, making the substitution, the t of n over 3 I replaced with t of n over 9 plus cn over 3. Plus, we still have an additional copy of Cn from the original equation. Now we're going to take that t of n over 9 we look at, and we notice we need to plug n over 9 back into the red barred equation. So let's do that. Plug n over 9 into the red barred equation. So that gives us t of n over 9 on the left-hand side is equal to t of n over 9 over 3, which is n over 27, plus cn over 9. Plugging that in, we're going to replace n over 9 with the right-hand side here that I just underlined in light blue. So let's make that substitution. We get t of n is equal to t of n over 27 plus cn over 9 plus cn over 3 plus cn. Notice we need to keep the cn over 3 and the cn from the other equation. So, just as we've seen with our chip and conquer type examples, the ones where we were subtracting things from t, here we see that we have something with t and then a bunch of terms added together. The something with t is a nice easy pattern for us to identify. We had n over 27, n over 9, n over 3. That's n over powers of 3. So this looks like t of n over 3 to the k. That's nice and straightforward. The other terms, underlined now in purple, I can express as a summation. So we can write that as, just like we saw in the past, the sum from I equals 0 to k minus 1 of the same sort of thing we're seeing with the t. Cn over 3 to the I here. Let's check that that makes sense. For I equals 0, we get Cn. I equals 1, we get Cn over 3. I equals 2, we get Cn over 9. The next thing would be Cn over 27, 81, and so on. So math seems to check out. That means for any value of k, we have that t of n, the left-hand side that we had still, is equal to t of n over 3 to the k plus that summation, the sum from I equals 0 to k minus 1 of cn over 3 to the I. Let's maybe write that a little bit neater to make it not so hard to look at. Write that as cn over 3 to the I. Now, we want to find out when does the recurrence terminate. So to figure that out, we scroll back up to the original problem, and we look for the base case. In this case, the base case was t of 5 equals c. So this stops once we arrive at that. So it stops when the thing inside of t, in this case n over 3 to the k, is equal to our base case, which is 5. To solve that for k, we multiply by 3 to the k and get n equals 5 times 3 to the k. Divide by 5, and we get n over 5 equals 3 to the k. And take a log base 3 of both sides, and we have k equals log base 3 of n over 5. So that gives us a value of k for when do we stop. We're then going to substitute that into our generic expression in terms of k there. So if we plug it in, we get t of n is equal to t of 5. We know that happens because we chose n over 3 to the k to equal 5. Plus the sum from I equals 0 to k minus 1 of cn over 3 to the k. Sorry, 3 to the I. Notice I didn't plug in k for the summation because it needlessly complicates the problem. We do know t of 5 is just c, so all we need to do now is analyze that summation. So we must analyze the summation from I equals 0 to k minus 1 of cn over 3 to the a. How can we do this? Maybe a reasonable first step is pull out the c times n. That has nothing to do with I, so we can factor it out. Cn times the sum from I equals 0 to k minus 1 of 1 over 3 to the I. That almost looks convenient. We're going to do one more algebraic simplification here. That's equal to Cn times the sum from I equals 0 to k minus 1 of a third. Let's write that a bit neater. 1 over 3 to the I. Why can I do that? Well, 1 to the I is always just 1. So this is like 1 to the I over 3 to the I, which we can write as 1 over 3 all raised to the I. Now this looks convenient, so we might remember, let's write this off to the side, recall, we have a nice formula. The sum from I equals 0 to n of r to the I is equal to 1 minus r to the n plus 1 over 1 minus r. Or we could remember that we know the complexity of that type of summation. But for now, let's do it the hard way. This equals Cn times, using that formula, I have r is equal to a third, and my n value, n with quotes around it, is k minus 1. So I have 1 minus r, which is 1/3 for this problem, to the n plus 1, but my n here is k minus 1. So that's just to the k, all over 1 minus a third. So this equals Cn times, maybe we notice some nice stuff. The denominator there becomes 2/3. But beyond that, there's not much I can do without plugging in a value of k. So let's plug in my value of k, which maybe we don't quite remember. So let's scroll up. Oh, it was log base 3 of n over 5. So let's plug that in while doing some other algebra at the same time. I can write this as 3cn over 2 times 1 minus 1 over 3 to the log base 3 of n over 5. That's a bit hard to simplify as it is, but I know I can rewrite this as 3 over 2 times Cn times 1 minus 1 over 3 to the log base 3 of n over 5. Because 1 to the log base 3 of n over 5 doesn't matter what the power is. 1 to any power is 1. And then we just have 3 to the log 3 of n over 5 in the denominator. Now we get some nice cancellations here. We can see that the 3 and the log 3, they're inverse functions of each other, so they cancel each other out. And I get that this is equal to 3 over 2 times Cn times 1 minus 1 over n over 5. Keep simplifying, and we get 3 halves Cn times 1 minus 5 over n The dominant term here, maybe we can finally identify that this is in theta of n. So, that's a bit of a long-winded way to get there, but the original summation from I equals 0 to k minus 1 of cn over 3 to the I is in theta of n. So let's substitute that. We get t of n is equal to c plus the summation we know is in theta of n, which now it's not too bad to see from here maybe. We could say, therefore, t of n is in theta of n. This answer is weird. Why is it weird? Well, it's weird because if we scroll back up to the original problem, what was happening here? We had a recursive call, t of n over 3, plus cn. So I'm going to write that down up here. T of n equals t of n over 3 plus cn. So we had that in the overhead of making any recursive call at all was cn, and then we do a recursive call, then we do a recursive call, then we do a recursive call. Now after making every single recursive call we need to, we still get that the total complexity is in theta of n.